All right. So this is the upcoming schedule for the class. Homework 7 is due on this Thursday, so it's only 3 days from now. Okay. And then 8 is due on Wednesday next week, so it's 6 days after 7 is due. And then so 8 will be visible to you guys from tomorrow or this after midnight tonight. Okay, if you want to work on that. 9 will be I'll set that up may probably sometime next week, early next week. Okay, so then you guys can work on that one. Then exam 3 will schedule to have it on the Friday towards the end of the month, the 30th. Okay. So finally, for the classroom surface disinfection, Isaiah and Morgan. Okay. For today. All right. So last time we start chapter 9 on linear momentum. So it's defined as let's see. So it's defined as the mass times the velocity. So then P is a vector. Okay, so momentum is a vector. So then if you have multiple dimensions like X and Y dimensions, you'll have to do that in X and Y directions. Okay. SI unit will be kilogram times meters per second. And we talk about impulse and momentum. So basically, impulse is defined as the force times delta t, the impact time. So then impulse should be also a vector. Okay, it has the same direction as the average force. And if you are doing differential form, then it's derivative of j equals to f times derivative of time t. Okay, impulse should have SI unit of newtons times second. All right, and then for the Newton's second law, when he initially proposed it, is in the form of change in momentum over change in time t. So in that case, if the net force is equal to 0, then change in momentum should be equal to 0. Okay, so that gives you the condition for conservation of momentum. If net force acting on the object is 0, its momentum is conserved. Okay, so then you can write initial momentum equal to final momentum. And then again, because it's a vector, so if you have x and y direction, then you'll write them separately. So momentum in x initial should be equal to momentum in x final, and then also the same for y direction. Okay, initial should be equal to final. All right, if you have multiple objects in a system, there might be internal forces between the objects, but because force comes in pairs, so the internal forces, they will be pairs of action and reaction force, so they will cancel out because they are in the opposite direction for the pair. Okay, so then in that case, if external forces is 0, then the momentum for the whole system should also conserve. So then you have to add up the momentum for each of the object. Initial should be equal to final, but however, the momentum for each of the object might be changing. So for example, P1F is not necessarily equal to P1 initial, okay? Or a lot of times it's different, okay? And then P2 initial and then P2 final, and most of the time they should be different from each other. All right, so today we are going to explore more in details of the different types of collision, okay? So there are actually 2 types of collision. So one is called elastic collision, and then the other is called inelastic collision, okay? But for inelastic collisions, there's detailed classification on that too, but we'll take a look on this terminology over here, okay? So for collision, it's defined as when you have 2 or more objects striking one another, all right? And then for time of collision, because usually when collision happens, the time of collision is very short. So then it's short enough that external forces can be ignored. Okay, so typically external forces are small compared to the what you have for the collision when they compared to the internal forces. Okay, and then because time is short, so then that for the more impulse to the system, you can ignore it. Okay, so when that happens, so in this class, unless otherwise specified, you'll consider a collision to be short enough so you can ignore the effect of the external forces. Okay, so that means when you see collision, when you see the word collision, you can apply conservation of momentum. All right. So, so then for the elastic collision is when the collision happens. So as I mentioned, when you see collision, then that means you can always apply conservation of momentum, right? So conservation of momentum is applied here. Now, the word elastic here means the kinetic energy is also conserved. Okay, so if you see elastic collision, that means you can apply both momentum conservation and also kinetic energy conservation. Okay, so kinetic energy conservation, that means initial kinetic energy is equal to final kinetic energy. Okay. Now, a lot of times when collision happens, a collision is typically an inelastic collision. That means you can only apply conservation of momentum, but not conservation of kinetic energy. Okay, so typically there's kinetic energy loss during a collision. That's most often happens. Okay, but for elastic collision, casually you will see a problem on that too. For inelastic collision, there's a special case called completely inelastic collision. That is when if you have two objects collide, then after collision, they stick together. Okay, so when that happens, you have the maximum loss in the kinetic energy. Okay, so the loss of kinetic energy will be maximum in that case. That's why it's called complete inelastic collision. All right, so those are some terminologies and a couple of different types of collisions. So we'll take a look at examples on elastic collision and then also an inelastic collision here. Okay. So again, for elastic collision, that you can apply the conservation of momentum. You can also apply conservation of the kinetic energy. Okay, so you can write out two equations. The first one is so for example, you have two plugs collide with each other along this frictionless surface. So then momentum of one plus momentum of two, that's total momentum. Okay, so then before should equal to after. So after collision, if you write as P1 prime plus P2 prime, so these two should equal to each other. So P1 plus P2 should equal to P1 prime plus P2 prime. Okay. And then also because it's an elastic collision, so you can apply conservation of kinetic energy. So if you write kinetic energy 1 plus kinetic energy 2 initial, that should be equal to kinetic energy 1 final plus kinetic energy 2 final. Okay, so we use prime there to denote the final status. All right. So then if you are given the masses of the two objects and then their initial velocities, then you should be able to figure out their final velocities. Okay. So when you write out these two equations, so this is the initial momentum, this is the final momentum, so they equal to each other. And then this is the initial kinetic energy, this is the final kinetic energy, they also equal to each other. All right. So if you are given the initial masses, you should be able to see. My touchpad is acting very weirdly. All right. So let's see. So if you apply conservation of momentum, you write initial momentum equal to final momentum. So you say m1 v1 plus m2 v2 equals to m1 v1 prime. So the prime denotes the final status, and then m2 v2 prime. Okay, and then you can write 1/2 m1 v1 square plus 1/2 m2 v2 square. That should equal to 1/2 m1 v1 prime square. Okay, so this is like that, plus 1/2 m2 v2 prime, and then square. Okay, so if m1, m2, v1, and v2 are given, then you can solve for v1 prime and v2 prime, right? Because you have two equations, you have two unknowns. Okay. So we can take a look on the algebra here. So the 1/2 here can cancel out because it's across the equation on the terms. Okay. So now from what we have here, you have a block 1 that is moving. So in this case, block 1 is moving and then hit on block 2, which is initially not moving. So block 2 was initially at 0. Okay. So then actually this guy, so then this term becomes 0 because v2 is there. And then this term becomes 0. Okay. So if that's the case, so then we can actually rewrite these two equations because now you have reduced terms. So m1 v1 then equal to m1 v1 prime plus m2 v2 prime. Okay, and then the second equation you should have m1 v1 square equal to m1 v1 prime square plus m2 v2 prime square. Okay, so now you have these two equations, and then from there you can solve for v1 prime and v2 prime. So to do this, you will write one unknown in terms of the other unknown, and then take that doing the substitution into the second equation. Okay, so from here you can write v1 prime in terms of v2 prime. Okay, so then you basically move this guy to the other side of the equation. All right, and then divide both sides by m1. Okay, so that will give you v1 minus m2 over m1 v2 prime. Okay, so I'm just skipping a couple of steps here, but you guys should be able to figure that out. Okay, so then after that you can take this expression in the place of v1 prime in the second here. So taking that expression over here. All right, so then you will have m1 v1 square on the left hand side, and then on the right hand side you will have m1 v1 minus m2 over m1 v2 prime and then square plus m2 v2 prime square. Okay, so now you have one equation, and then the unknown, the only unknown in the equation is the v2 prime. Okay, so you can solve for v2 prime here from this equation, but it will be a quadratic formula because you have v2 prime square. Okay, all right, so let's see. I'm going to divide everything by m1. Okay, so then divide this by m1, get rid of m1 there, and then this one divide by m1, get rid of that guy. But this one you have m1, m2 over m1, okay? So v1 square equals 2. Now you just square the parenthesis here. There are two terms. It becomes v1 square minus twice v1 times this guy, m2 over m1 v2 prime, okay? Plus this guy square. So m2 over m1 v2 prime square. And then plus m2 over m1 v2 prime square, okay? I think it's a little bit tedious, but you guys should be able to do this by yourself. Okay, so you can see here, this one and this one, they are the same, right? So that will cancel out. Okay, so it actually doesn't look like that complicated. Okay, because now you have v2 prime here, you have v2 prime square here, you have v2 prime square. So you can actually cancel out one v2 prime, and then okay, so then it will not be a quadratic formula, okay? All right, so I'm going to put this guy to the other side of the equation, so it becomes 2 times, I'm going to put m2 over m1 first, and then v1 times v2 prime, okay? This guy here, that equals to here, I'm going to do m2, let me see, m2 over m1 square, okay? And then v2 prime square here plus m2 over m1 v2 prime square. Okay, so I think we can have further cancellation over here. So this term, m2 over m1, this is m2 over m1 square, and then this is also m2 over m1. Okay, so we can cancel out m2 over m1, and then one of this two, so it becomes just m2 over m1. Okay, and then also you will notice that there's v2 here, there's v2 or v2 prime here, v2 prime square, v2 prime square there. Okay, so you can get rid of v2 prime, and then that reduces the order. Okay, so what's remaining right now is 2 times v1 on the left hand side equals to m2 over m1 times v2 prime plus v2 prime. Okay, so then this is 1 plus m2 over m1 times v2 prime on the right hand side, and then this is 2v1 on the left hand side. Okay, so then for v2 prime, you'll be able to solve for that. That should be 2 times v1 over 1 plus m2 over m1. Okay, and then you can rewrite this guy. So if you multiply m1 here on the top, and then also m1 here at the bottom, but remember you should put parentheses here. Okay, so that will become v2 prime will become, so this is twice of m1 v1 divided by, okay, on the top is 2 times m1 v1. At the bottom here, it should be 1 multiplied by m1 should be m1, right? Plus m2 over m1 multiplied by m1 should be m2. Okay, so that should be your v2 prime. And so then for v1 prime, it's gonna to be that guy there up there. Okay, so v1 minus that is v1 minus m2 over m1 times the v2 prime. Now you can take this expression times the v2 prime, which is 2 times m1 v1 divided by m1 plus m2. Okay, I can see that this m1 and then this m1 will cancel out. Okay, one on the at the numerator, the other one at the denominator. Okay. All right. So then this is V1 minus twice M2 V1 over M1 plus M2. Okay. Now you can rewrite this term here over here. You can do V you can do M1 plus M2, M1 plus M2, right? This is basically give you 1 multiplied by V1. So this is the first term. Okay. Just put that in that form and then minus the second term M1 plus M2 of 2 times M2V1. Okay. By doing this, you can have the common denominator. So then M1 plus M2 at the bottom here. Now M1 plus M2 times V1 minus twice of M2 V1. That will give you M1 minus M2, okay, times V1. All right. So this will be your V1 prime. This is your V2 prime. The final velocities of the two. Okay. So once you have that, so it's basically then this guy here, okay? This scenario over here. So you have one block moving, and then this guy initially, that if it's at rest, then that's what we have for the solution, okay? But you might have this guy as moving as well, okay? So then that's another scenario you have to consider. But basically, the next example is exactly the same as the assumption we made, okay? So the car one here, a small car, stopped at the intersection and then it's rear-ended by a second truck or second car there. So so then in this case, your M1 is the 1702, okay? The 1720 kilogram, and then your M2 is 732. All right. So V1 is the 15.5, V2 is the 0. So then you can apply these two to solve for the final velocity. Okay. So it says if the car was in neutral and the brakes were off, so that the collision is approximately elastic, find the final speed of both vehicles. Okay. So then this is what you have. All right. I think I should have start from the beginning here on the problem. So you will start with these two equations. Okay. You can work out for the algebra. You can come to these two expressions for the two final velocities or the two final speeds. Okay. So then at the end, you're just plug in the numbers here. So V1 prime should be equal to M1 minus M2 over M1 plus M2 times V1. Okay. So then it's this 7020 minus 732 kilograms divided by 720 plus 1720 plus 732. All right, they should all in kilograms, and then times this initial speed of 15.5 meters per second. Okay, that will give you the speed as 6.25 meters per second. Okay, so this is for the car. Oh, this is for the truck. Sorry, truck is the object one, and then for the car, V2 prime is going to be 2 times M1 V1 divided by M1 plus M2. Okay, so 2 times M1, the 1720 kilograms times the 15.5 meters per second divided by 1720 kilogram plus 732 kilogram. Okay, that would be 21.7 meters per second. So this is the speed for the car after the collision. Okay. So again, this will be the full solution for this example. So you start from the beginning, write out two equations because it says the collision is approximately elastic. So then you write out the conservation of momentum for the collision, and then the conservation of kinetic energy for elastic collision. Okay. So the problem gives you M1, M2, V1, and V2, and then you are solving for the final speeds of the two. Okay, so just assuming this is the first one is a truck, and then hit on the smaller car. Okay, in that scenario, something like that. Okay, so this is M1, V1. This is M2 and the V2. Okay. And then solve for M1, solve for V1 prime and V2 prime algebraically. Then plug in the numbers at the end. Okay. All right. Any questions you guys might have? So, if not, then we'll take a look the scenario of the inelastic collision. Okay, so when inelastic collision happens, then you only have conservation of momentum. Okay, so you will not be able to apply conservation of kinetic energy here. So you can only write down one equation, which is P1 plus P2 equals to P1 prime plus P2 prime. Okay. So in this scenario, they are identical masses with the same speed in opposite direction. So then initial momentum should add up to be 0. Final should be add up to be 0. Okay. Now you can see the kinetic energy initially is mv squared. It's 1/2 mv squared from each of the block. So it's mv squared. But the final, because when they collide for inelastic collision here, they will stick together in this particular scenario. So then final kinetic energy should be 0. Okay, so the two is not equal to each other. Okay. We'll take a look on this example here. So it says an air track cart with masses of 0.32 kilogram and an initial speed of 0.85 meters per second collide with and stick to a second cart that is at rest initially. If the mass of the second cart is at 0.44 kilogram, how much kinetic energy is lost as a result of the collision? Okay, so it tells you there's a collision, and then it tells you after the collision, the two stick together. Okay, so I think you guys should be able to do this. Just apply conservation of momentum here to figure out what's the final speed of the two. Okay, when they stick together, and then you can calculate what's the final kinetic energy of the two. All right, and then minus the initial kinetic energy of the two together, and then you'll see how much kinetic energy is lost. Okay. So you guys can give it a try, and then we can take a look on the solution together in a few minutes here. All right. So before collision, M2 is 0, or V2 is 0, M2 is 0.44, M1 is 0.32, and then V1 is 0.85. Okay, after collision, they stick together, okay? So for the second car, it probably has an extra weight on it, okay? So it's heavier. So because it says they stick together, right? So when the two actually stick together, then it's not going to be elastic collision, okay? Then it's going to be total inelastic collision because the two, when the two stick together, actually the last of the kinetic energy will be maximum, okay? So if you remember when we discuss about different collisions, so that falls in the category of the inelastic, totally completely inelastic collision, okay? But you can still apply P total initial equal to P total final, okay? So that's the total momentum initial equal to total momentum final. So initially you'll have M1 V1 plus M2 V2, okay? Equals to M1 V1 prime plus M2 V2 prime, okay? Now the two, when the two stick together, then the two should have the same speed, right? When the two stick together, the final speeds are the same, so you can call it as V. So then it will be M1 plus M2 times V, all right? Now this guy, V2 is 0, so this guy will be 0. So it's going to be just M1 V1 equals to M1 plus M2 V, okay? Where V is the common final speed. So you can calculate for the V. Now you are looking for the last of the kinetic energies, right? So that means you are looking for kinetic energy final minus kinetic energy initial. Okay, and that equals to last of kinetic energy. Okay. So if you didn't know this, so when we talk about change in kinetic energy, we do actually the other way around. Sorry, we do initial minus final. Okay, that refers to the last of it. When we do change of a quantity, we always do final minus initial, okay? But when we talk about the last of some quantity, then you do the initial minus the final, okay? So that's the difference here. Anyway, if you are looking for the last of it, so then you'll be doing 1/2 m1 v1 square, right? Plus 1/2 m2 v2 square initial. So this is the initial kinetic energy minus the final kinetic energy, 1/2 m1 v square of v1 prime final plus 1/2 m2 v square, okay? So you need to know the final velocity, right, of the two together in order to calculate this. All right, so then your v is equal to, you divide both sides by m1 plus m2, so m1 v1, okay? And plug in your numbers, 0.32 kilogram times 0.85 meters per second divided by 0.32 kilogram plus 0.44 kilogram. And your final speed of the two together will be 0.358 meters per second, okay? Then plug in the numbers here. So the first one will be 1/2 0.32 kilogram times the initial meters per second square, right? Plus this guy should be 0 because initially the second car is at rest. Minus 1/2, you can combine the m1 and m2 together, okay? Because the v is the common speed, okay? So then that gives you the last of your kinetic energy. It's going to be 0.067 joules there, right? If you are looking for a change of kinetic energy, then it will be minus, okay? All right. Okay. All right. So I think I have mentioned that so for collisions, many times it's not just as simple as one dimension. It could be two-dimensional or sometimes it could be three-dimensional. But we'll take a look on the two-dimensional collision here. Okay. So when you have two-dimensional collision, for example, here, so this guy collides with this guy. So this is initially at rest, okay? So when it happens, the collision happens, it might not be necessary like the center of mass here is collide right on the center mass of the second one, okay? So then after the collision, this object one is going in that direction, object two is going in that direction, okay? So in this case, then you'll have two-dimensional collision here, all right? So when that happens, when collision happens in two-dimensional, then you'll be doing momentum x direction initial equal to momentum x direction final. And then also a second equation you can apply is the momentum in y direction initial is equal to momentum y direction final, okay? Now keep in mind, because there's collision, so that this means the total momentum here, and then initial, and then this is total momentum final, okay, in x direction. And then total momentum in y direction initial equal to total momentum in y direction final, okay? All right. So we can take a look on this example here. Okay. It says a falcon is diving at 28 meters per second in this direction, okay, with a horizontal of 35 degrees. So that means it's below horizontal in that direction, okay? It catches a 0.65 kilogram dove, which is flying in this horizontal direction, initial velocity. And then I guess caught it, and then after the collision together. Okay, so it says it's asking you what's their combined velocity after the impact. Okay, so it's asking you what's the combined or the common velocity. So the two will stick together after collision. Okay, I'm thinking for the time, because of time limitation, we will just take a look at the solution together. Okay. So this is a two-dimensional collision. Yeah, looking for the final velocity of the two. Okay, so that means you can solve for the x component and then y component, right? And then you can write them in the term of, so velocity equals to x component plus the y component in j. Okay, you can write in that fashion, or you can work out for the magnitude and then specify the direction. Okay, so either way, so either doing this way or doing it this way. Okay. All right. So we can write out two equations. Sorry. You can do components method, like specify that in x component and y component. You can also solve for the magnitude and then direction. Okay, specify the two. So either way. So we are going to just write out two equations because this is a two-dimensional collision. So that means momentum x directional initial is equal to momentum x direction final. Okay, and then momentum y initial is equal to momentum y final. Okay, so for the x direction first, initial x momentum is going to be equal to m1 v1 x plus m2 v2 x. Okay, now the Falcon, I don't think I'm good at drawing birds, but you can imagine like that. So it's V1 is in that direction of 35 degrees, okay? And then M1 is 1.8 kilogram. This is 28 meters per second for the magnitude, that's the direction. So this is 1.8 kilogram times V1x, okay, V1x. So it'll be the V1 cosine of the 35 degrees, okay? In this case, it says downward, so that means negative 35, okay? But cosine of negative will be still positive. M2, so M2 for the small dove, it's going in that direction. V2, it's given as the, just in the horizontal direction, okay? So 7 meters per second in the horizontal direction. So then times M2, M2 is given as 0.650 kilogram. So 0.65 kilogram for the M2. V2x will be just that guy, okay? V, because that's the x direction only, all right? So V1 is 28, sorry, 28 meters per second there, times cosine, all right? And then plus that. So this is your initial momentum in x direction. So 45.84 kilograms times meters per second, okay? And for the final, px final, that should be m1 plus m2 times the vx, right? So if this is v, the final speed, because they are together now, so then vx, okay? So then you can solve for your vx. So this two should be equal to each other. So you can set up that, oh, this is equal to the 1.8 kilogram plus 0.650 kilogram times Vx, right? So then that equals to this guy, because this is final, this is initial. Those two should equal to each other. Okay. So your Vx then would be 45.84 divided by this two add up to be 2.450 kilogram. Okay. So then the x component would be of the velocity would be 18.7 meters per second. Okay, so this is your x component. You can do the same to the y component. Okay, so py initial is equal to m1 v1y plus m2 v2y. m2 v2 v2y should be 0 because for the Falcon, its initial velocity is just in the x direction. Okay, so the y direction is 0. So this is 1.80 kilogram times v1y. You'll be doing the magnitude 28.0 meters per second times sine of minus 35. Okay, so it's the v1 sine of the theta plus 0. So this would be negative 28.90 kilogram meters per second. Now, py final will be equal to m1 plus m2 vy, final y component, okay? So then this will be, again, the m1 plus m2 will be that guy, so 2.45 kilogram times vy. So you'll set up, again, this equal to that, okay? So that will tell you your vy will be equal to minus 28.90 kilogram meters per second over 2.45 kilogram. That would be negative of 11.8 meters per second. Okay, so this is the y component, this is the x component. All right, so it asks you what's the final velocity of the two together. So you can just write in this form here, 18.7 meters per second, right, in I direction, minus 11.8 meters per second in the j direction. All right, because it didn't ask you specifically what format, so you can express in this way. Okay. All right. So I think we just finished this in time. Okay. So we'll stop here for today.